Charge is an intrinsic property of the electrons and protons that make up the world. Charge objects interact such that charges of opposite signs feel an attractive force between them, while charges of the same sign feel a repulsive force. One of the things that's special about charge is that it's conserved absolutely. You can't ever create or destroy a single charge, either positive or negative, but you can create or destroy pairs of charges with opposite signs. PET scanners in hospitals work because antimatter electrons, known as positrons, they're positively charged, collide with ordinary negatively charged electrons and completely annihilate. If we were keeping track of the charges, we could write this as 1 plus minus 1 equals 0. Charge is also quantized. All the charges we're ever going to see will be a whole number multiple of the charge on the electron. It's not important in this class, but just in case you read it somewhere, there are subatomic particles known as quarks, and they can have charges that are multiples of 1/3 of the electron charge. It won't matter for us because you only see these things in triplets or in plus-minus pairs, so that the total charge on any particle made up of quarks is still an integer multiple of this same fundamental unit of charge. In the metric system, the MKS unit of charge is the Coulomb, capital C because it's somebody's name, and the fundamental unit of charge on an electron is 1.602 times 10 to the negative 19 coulombs. Negative, of course, and the reason is Benjamin Franklin basically made the wrong choice as to what was doing the moving in an object. So all electrons have negative charge. If we take a piece of amber and rub it with a cloth, what we find is the cloth loses electrons to the amber. That means the cloth becomes positively charged, the amber becomes negatively charged. We could do this with other things like glass rods and rabbit fur, silk, other things like that. Everything that's macroscopic and neutral is composed of an equal number of positive and negative charges, and we can use friction to separate some of these electrons from their atoms. A really, really small proportion, and that's what charges things. We can also look at the concept of conductors and insulators. Conductors are things where the electrons are able to move around freely. That means, in general, metals. They can carry an electric current. Insulators don't allow the electrons to move freely. You can understand this with the atomic theory by realizing that in a metal, each atom gives up 1 or 2 electrons that will be part of the material as a whole instead of being attached to a particular electron, attached to a particular atom. The electrons still can't leave the metal, but they no longer have to stay in the neighborhood of their original atom. In an insulator, on the other hand, each atom holds onto its electrons and they're not allowed to move from atom to atom. And trying to divide everything in the universe into either conductor or insulator is really a ridiculous approximation, because the real measure of difference between these things, which is resistivity, how well does it act like a conductor or insulator, the range of this is about 10 to the 24, so 24 orders of magnitude between the best conductors that aren't superconductors and the best insulators. So it's ridiculous to reduce that to a binary yes or no, it conducts or it doesn't. Additionally, it turns out that even things that we're pretty sure are insulators, like plastic, rubber, and glass, will still conduct electricity if we put them in the right conditions. Even with all these limitations, we can still get some use out of this idea of conductor or insulator, at least for this lesson. When we have a charged object, we can transfer that charge to another object. One obvious way to do it is contact, which means bumping them into each other. But another way to do it is induction. If we have our positively charged rod that we got from the animal fur experiment and move it near a conductor, like a metal ball, what we'll see is charges in the conductor are free to move, so negative charges will come over to the side where the positively charged rod is. Positive charges will want to stay on the other side. Now, we're going to pretend like they're both mobile for a lot of effects. We're going to play like positive charges can move to the right and negative can move to the left, even though really, in solids, all that ever happens is negative charges move. So the whole sphere is neutral, but we now have a positive side and a negative side. Now, We do talk about the movement of positive charges. That's called the conventional current. It's what physicists use, and again, it goes back to Franklin getting the charge on the electron wrong. It's not what's happening physically, but if we have a positive charge moving to the left, it's going to look exactly the same as a negative charge moving to the right. The only thing that will distinguish them is something we'll talk about in a few weeks called the Hall effect. Physicists, though, stick with the conventional current, meaning we pretend like positive charges are doing all the moving.